omega t bar minus omega t. This is same as u t bar, like the interior of the domain and its boundary minus you just remove the interior. So that is basically the boundary of the domain. Here we there is an expression to express in this form because the boundary is unbounded. We don't know what is the boundary. So that's why we are writing omega t bar minus omega t. Another we could simply write, oh, so this is del omega t. So that is the reason why we are writing in this way. This was del omega cross 0 comma t, and uh, the boundary condition here is like the initial condition, like at t equals to 0 the whole region, and then the next time when t is varying, then we are taking the boundary of the domain. So just try to understand it physically, what its geometrical explanation. So just try to understand its geometrical explanation, or you can say geometrical interpretation. See, like how I define this, just take a look. I define this axis as t axis, like t was varying vertically.
Excuse me, teacher.
Yeah.
The symbol at the over frontier. No, es U subset R to N, differential tilde. What's the meaning?
You're talking about this one?
Yes.
Don't get confused, my thing, so just wait. Now is it fine? This is just understand it geometrically, and then you will get that. So how I wrote the geometry. So I said that in three dimension, in n dimension, if this is denoting your space variable, suppose this is the surface, so it is going to be a hypersurface in n minus 1 dimensional space. And if we are giving heat to this end of the rod, so where T is varying? T is varying in the vertical direction because you are giving heat here or here. So it will be either going this direction or this direction. So this is basically temperature axis, isn't it? This is basically temperature because temperature is going, and this axis is going to be your spatial axis. Spatial axis, and this is temperature axis. Now we are defining the this is domain. Is it clear, Roberto? But how am
Yes.
yeah, so now I am coming to the boundary of the domain. Like every time when we are writing either Laplace equation or heat equation, we have to define the boundary and the initial condition. Since this is a heat equation, so the temperature of the rod is varying with time. This is a time, this is time, sorry. This is time x.
Time.
Yeah, where temperature is varying, because here you will start to give the temperature and it will vary with the time in this direction. So the time will be varying in this direction. I just did a mistake, sorry. So spatial axis and time axis. Now your temperature U is varying with time as well as it is varying with space variable. It means U is function of T and all the space variable, isn't it? So when t will be 0, you will have initial condition. When t equals to 0, you will have initial condition. And also we know that when we are talking about the heat equation, there is an initial condition and also there is a dissipation of the heat. There is a dissipation of the temperature through the boundary, isn't it? Like if the boundary is not isolated, so some heat goes outside of this rod through this. It means it has some boundary condition and it will have some initial condition. So initial condition, we used to write t equals to 0. As you asked us yesterday, we can simply write t not as 0. At what time you are starting, it doesn't matter. It is just a simplification that we are taking t equals to 0 just for the sake of convenience. So t equals to t naught or t equals to 0 is going to give us initial condition, and since the temperature is is also going to dissipate through this boundary. So we also have some boundary condition. It means we have mixed condition. We have mixed condition. So that mixed condition, here you can see that how we are defining the boundary condition, how we are defining the boundary condition. So there is the point. If T is varying, so we are taking the boundary of the cylinder, like the boundary of the cylinder. This is the boundary, this and this is the surface boundary. And when T equals to 0, when union, when T equals to 0, then we are considering the whole domain. Like T equals to 0, the initial data. So how we define the condition U x comma 0. Now x bearing on the whole domain, isn't it? So this is one initial condition, and the other condition we define U L comma T is something, some function of f, say some function of z. Now T is belonging to 0 comma T, and this L is going to be boundary. So can you relate this thing written here?
What? Excuse me, can you repeat the question?
I am saying that this was your initial condition where x is varying over the domain omega or domain u, whatever you are denoting. And when we are taking the boundary, suppose you are taking L, the height of the cylinder is L. So you are taking at L, U, L, comma T, it means you are on the upper boundary. And similarly here you are saying that R equals to A, unlike on this left boundary, left wall. So at that moment T is going to vary, but the boundary is fixed. So L is coming from delta of the omega. It is varying. So can you relate these two conditions to this equation? This is a general way to write it.
Okay.
No, I'm asking, can you relate that? Yeah, this is the same way to write it. Everything is clear?
Yes.
Okay. Carmelo, do you have any doubt in this one?
No, all is clear.
So this is the way, like, I thought this might be a confusion, but since now I am explaining it geometrically, so it should be clear why we are defining the boundary in this way. So since it is a heat equation, you will be having a mixed condition, a mixed initial boundary condition. So that's why this is the way to write it. Okay, let's go to the strong maximum principle. If I am just asking a general question to all of you, what is the integration of this heat kernel?
One moment, please.
We already have discussed in the last classes. What is the value of this integration?
1?
Okay, so this is a normalized kernel, so the value, I was just reminding you because I am going to use this, I cannot tell you at each step, so I just asking just, yeah, it's fine with letting you know. So we know that if we have a heat equation, then the solution of this heat equation can be written as kernel x t y, or yes, you can say u y comma s dy ds. You know that we can write the solution in the terms of the heat kernel, where this is the value of the function u defined at some time t, defined at some time, can say s. So this initial value is supported by this heat kernel. This initial value is supported. I am saying that initial value because since it is a heat equation and the variable u is varying with time t. So that's why we are saying it. Okay, so this is initial value, initial data is supported by the heat kernel k. Let me take a look. I forgot the symbol what I mentioned in the last class. Yeah, so it was the same. Yesterday we were talking about the weak maximum principle. So the weak maximum principle was U was the solution of the operator del t plus L, where L was the operator like the second order derivative summation I comma j varying from 1 to n d I j plus it was alpha I j plus summation I varying from k varying from 1 to n beta k b k plus some constant c of k. So this constant ck was playing an important role, but here we talk about the solution of the heat equation in UT. Like we are simply taking this operator del of t equals to Laplacian. So del t over equals to Laplacian of u. So del of t minus Laplacian operator. Simply there is no c. We are independent of this c. The operator is this del t minus Laplacian. So we are going to talk about this operator today. So this does not contain any constant beta, k and ck. So that's why we are going to talk about the strong maximum principle for the heat equation. But before proving this theorem, I would like to write a statement, and this is the part of your assignment you are going to prove. let u belongs to C1 to ut, it means u is a function that second order derivative is continuous inside of the domain ut. Solve the heat equation. If it solve the heat equation, it means ut minus Laplacian of u is 0. Solve the heat equation. Then u of x comma t is equals to 1 over 4 Rn e x comma t comma r u y comma s modulus of x minus y square over t minus s square divided over ds, where this will be your heat kernel. This will be your heat kernel. So you already have proved the mean value property for the Laplace equation. In the Laplace equation, it was 1 over volume of the ball at center rate r integration boundary of Br dr. It was something like that. I don't remember exactly. Is it this, Camilo? Roberto is seeing his notes. Camilo, do you remember what was the mean value theorem for the Laplace? It was something like this.
No, sorry, I don't remember exactly the formula.
So it was 1 over volume of the ball centered at radius r. So this is going to be same here into, I think here it was velocity potential it was. I don't remember exactly. But this is also the derivation is coming from the same. So this is the part of your assignment. You have to prove it. Next, since we are going to prove this theorem, let's again draw the same figure. Assume this is the initial axis. So there is a point x naught.
Teacher, I don't know if you can see.
Yeah, exactly. So this is the this is volume del br integration del br u. Yeah, this was the case. Yeah, you're right. So this is also defined in the same way, like 1 over volume del br integration over br u dy. So this was the case. It was a volume integral dv. So this is the case, yeah. And here, if you were taking volume of br, so it was going to come as the boundary of br integration over the surfaces. So this was the mean value theorem, which we have proved, and we have pretty much idea about this. So this is the time axis. This is the spatial axis x naught. So this is t equals to t naught, suppose. And when you take the cylinder, it is not a circular cylinder. It can be any cylinder like this. So suppose you are in 3 dimensions. This axis is time axis, and you are taking other 2 axes, like this axis is x axis and you are taking y axis. So this will be a surface, isn't it? This part will be playing the surface. So this is a surface that is lying in the spatial coordinate, like if it is x and it is y axis. So this surface is lying in the x y axis, and the x naught t naught lying in that plane. Do you prepare notes every day, Roberto?
What?
You prepare notes in Quaderno. You
Yeah.
escribe. I don't know.
You say in English. Don't worry. I understand someone.
Yeah, so you write every day in the notes.
The most important, or for example, something that I think I don't understand good, I take the note about this, and after I search in the book.
Ah, that's nice. Okay. So there is a remark. It says that if U attains its maximum at an interior point, then U is constant at all earlier times. So this is the remark we already know, but we are also going to see the proof again for the strong principle. If U attains its maximum or minimum at an interior point, then U is constant at all earlier times. So here can you see that when we are talking about that U is attaining its maxima or minima at interior point, then U is constant at all earlier times. At all earlier times. So this is the most important thing which it is saying. So what it is saying that if U is attained at so suppose U is equals to maximum of U equals to capital M and this is belonging to x comma t. This x comma t is belonging to the interior of the domain ut, then U is constant at all the earlier times. So U of x comma s is again equals to constant and that constant will be equal to that maxima at all s less than t. At all earlier times like time less than or equals to t, it is going to be constant. So this is something different. It is not exactly the same what we have studied in the previous literature. It is talking about the constancy of the solution u at earlier times, like before t, it is going to be constant. So this is an intuition towards the interpretation over the variable t that the solution will be constant on the time interval 0 comma t naught provided the initial and boundary conditions are constant. Because if the boundary condition or initial condition are not constant, like suppose at one boundary it has another value and on the other boundary it has another value, and you are saying that the solution at the earlier time is constant, so that is the consistency of the solution, that if it is not constant on the initial and boundary data, then you can't say that the solution is going to be smooth, because if it vary on the initial and boundary condition and it is constant in between the times, it means there is no consistency in the solution. So provided the initial and boundary conditions are constant. However, if you calculated the value of the function u, that is the maximum of u at x comma t is capital M, then u is going to be constant at all s less than or equals to t, like u of x comma s is equals to constant. However, when t is, suppose this is t naught, t is greater than or equals to t naught, we can't claim anything. The solution may vary in that scenario. However, the solution T naught k T naught may change at times T is greater than T naught, provided the boundary condition alter after T naught. Let's prove this. This was just an illusion of the things which we have studied. So there is also a proof of this statement. There is also a proof of this theorem. Suppose there exists a point x naught comma t naught belonging to the interior of the domain ut with u x naught comma t naught is equals to m, and that is the maximum of u over all the domain, like ut is closer is ut union its boundary. Then for all sufficiently small r greater than 0, e x naught t naught comma r will be contained in ut. What is the definition of e x t naught? Let me write the definition and then I am gonna explain this. Yesterday we wrote the definition, isn't it? Okay, if it is not written, then we can write it again. So E x comma t comma r is a region in space and time variable where belonging to r n plus 1 such that s is less than or equals to t and phi x minus y t minus s is going to greater than or equals to 1 over r. So how you will be defining E x naught t naught comma r? Suppose you took this x naught t naught and now I am saying that this is the collection of all the points in space and time variable such that this s is less than or equals to t. S is less than or equals to t, like before the time t naught, before the time t naught. So when you will be defining here E x naught t naught r, so it will be coming like covering this region before the time t equals to t naught. And now we may employ the mean value property to write the solution at that surface which is containing x naught t naught u x naught comma t naught is equals to 1 over 4 rn integration over e x naught t naught. Roberto, could you please mute yourself? U y comma s modulus of x naught minus y. Earlier it was x minus y. Since we are taking the ball, we are taking the heat ball at the center x naught comma t naught with radius r. So since it is not a circular, so we are defining this ball in n-dimensional space. We are defining this ball in n-dimensional space. So it is not going to be a sphere. It will be a n minus 1 dimensional hypersurface. Its surface will be a n minus 1 dimensional hypersurface, and this is exactly not ball. This is a closed region. This is a closed region that has a surface and that is centered at x naught t naught r, because we are defining the surface of the cylinder like this. We are not saying that it is a circular cylinder. We are saying that it is a cylinder and its variation can be like this. It is not always round. If it was a circular cylinder, so the surface was going to be round. But since we are not sure about the geometry of the cylinder, so that's why I say okay. We are not saying it is a ball. We are saying that we are forming a structure which is covering all the surface, all the core area of the cylinder, and we are replacing that with, we are denoting that with E x naught T naught R. By mean value property, and the value at x naught T naught is by mean value property, if we remove this, then what is the value of this integral? What is this term? Isn't it this is kernel with heat kernel with this term?
Yeah.
And if we remove this, then what will be the value of the integral? This is normalized.
Yeah. 1.
Yeah. So I am saying that this integration is equal to 1. This integration is equals to 1. So for this integral to be equal to a constant capital M, what kind of property it should hold? It should hold that uy comma s in this domain should be exactly M, should be exactly this constant M, then it will coming outside and this will be giving it us unit, isn't it?
Yeah.
So in view of the above normalized form, the heat kernel, say this is your equation number second, say this is equation second equality in equation second holds only if u is identically equal to m within this domain x naught t naught r, and consequently we can say that u y comma s is equals to capital M for all y comma s belonging to E x naught t naught r. Now it means u, if u is attaining its maximum value inside of the domain, then when we are drawing a ball, or you can say that when we are taking a continuous region centered at the point x naught comma t naught with any radius r, not exactly radius, it can be anything like which is covering that area. U is constant in all the region, and when you will use the continuity property of the U, then you can extend this E x naught T naught R to the whole domain by just connecting with the line segment like what we used to do, and then you can say U is constant in all the domain. Again, what you will do, you will draw this kind of heat ball with a larger radius, again with a more larger radius, and then you're saying that even in that larger radius it is going to be constant because of this property of the normalized form of the heat kernel. So we can say that U is going to constant in all over the region as soon as you attain its maximum value inside the domain UT, because every time when we are talking about the domain UT, so this is an open set, isn't it? This is an open set and U is continuous in that open set. U is continuous in that open set. So if you are taking an open set, so can we say that we can draw a ball where it is going to satisfy this property, and using the heat kernel property we are deducing that U is going to constant in that open ball or in that open region. So because of that U is constant in this region, again we will connect another region with a line segment and we can say that, oh, it is a continuous domain, this there is no gap in this domain, so U is going to be constant in the other region, and similarly you can connect all the region like what we did. But still, let's write the same thing what I am saying here. Draw any line segment L in UT connecting x naught comma t naught with some other point y naught comma s naught belonging to UT with s naught less than t naught. Now, why I am saying that this S naught is less than T naught? So there is a reason. We can only talk about those times which are earlier than this time T naught, because as soon as the time will increase, we can't say anything. We can only talk about the earlier times, which times we have covered. We cannot analyze any times in the future. When it is boundary, then we can talk about, but when it is evolving in the time, then we cannot talk about the future because we don't know the future. So we can talk about the condition before the time t naught. So draw any line segment capital L in UT connecting x naught comma t naught with some other point y naught comma s naught, where s naught is always less than t naught. And now consider R naught is equals to minimum of S is greater than or equals to S naught, such that U of xt is equals to M for all points x comma t, such that S is less than or equals to T is less than or equals to T naught. Now this minimum is possible because U is a continuous function. So since U is continuous, the minimum is attained. Assume R naught is greater than S naught, then U of Z naught comma R naught equals to M for some point Z naught comma R naught on this line segment intersection in the domain because of the continuity. So when we are saying that we are connecting this point x naught t naught, let's draw the figure just to visualize those things. This is another point, why not comma s naught, because we are taking s naught should be less than t naught. We can talk about the earlier times, we cannot talk about the time in this domain. So we took another point, why not comma s naught, just earlier to x naught t naught, and u is continue the same. Now assume that this r naught is greater than s naught. So R naught will be coming at some point this. So this will be point of G naught comma R naught, where R naught is greater than S naught but it is less than T naught. So since this is a continuous line segment, so as soon as you will be increasing Ex naught T naught comma R naught, the value at this point is going to be equals to M. So u of z naught comma r naught is going to be m at some point g naught comma r naught on L intersection ut. So the whole domain is ut and this is the line segment L. So at L intersection ut, where this point is lying, like z naught comma r naught is lying on that line segment. So using the continuity property of the function u is going to attain the same value capital M. And so u is equals to m on e g naught comma r naught. Or now what we did, we were considering the heat ball at x naught comma t naught with radius r. Now using the continuity property, we can say that if we are taking this point g naught comma r naught and taking the radius r, then at this heat ball, that is basically E z naught comma t naught over r, u will be equals to m even on this ball for all sufficiently small radius greater than 0. And since this contains the line segment L intersection R naught minus sigma intersection T intersection R naught for some small sigma is greater than 0, we have a contradiction. So it is saying that, now just take a look. This E J naught T naught, no, J naught R naught comma R, that is another ball and it is plotted with a very small radius R, and it will also contains the line segment L intersection. You will take this R naught and R naught minus sigma, like R naught minus sigma will be coming on this way and this way. So it is giving us a contradiction that there is a minimum value. However, we can say that there is no minimum value, there is a maximum value we are getting. That is not possible. So it means we are getting a contradiction. So what we have to do, there will be no a minimum value, there will be a constant value that will be m and that will hold in the whole domain. So we have a contradiction. Thus R naught is equals to S naught and hence U is uniformly equals to M on this line segment. U is uniformly equals to M on this line segment. Even without this analyzation, we can say that because of the continuity of U, when we are taking any continuous extension of this heat ball, u is going to have the same value. It means u is going to have the same constant value on all the line segments which will be connected to this domain Ex naught T naught. Now we are going to talk about the strong maximality of this function u. So let's see. The second condition. Now fix any point x belongs to u and any time t that is basically less than t naught, there exist points x naught, x1, comma dot dot dot, xn equals to x such that the line segments in Rn. We are just writing the extension like what I said, that this you took this E x naught t naught comma r with the center at x naught t and t naught and the radius r. You took this hypersurface. Now we connected a line segment by taking a point y comma s where s is less than t naught, and we said that u is going to give the same value at this line segment because of the continuity. So in this way we can extend this line segment from the bottom to the point t naught, because we cannot talk about the further time, that is time t greater than t naught. We can just talk about the time less than t naught. So we can extend this line segment to the bottom of that cylinder in all the direction, and we can say that okay, so using this property we can say that u is going to get the same value at all the line segment, and because of the continuity of u it will have a constant value earlier than time t naught. So I am just writing the same statement. Now fix any point x belonging to the domain U and any time earlier than t naught. There exist points x naught, x1, comma dot 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 a general x such that the line segment in Rn connecting xi minus 1 to xi lie in U for I varying from 1 to dot 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 n. This follows since the set of points in U which can be so connected to x naught by a polygonal path is non-empty, open and relatively closed in U. Now select times t naught greater than t1 greater than dot 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 greater than tm equals to t. Then the line segments in R n plus 1 connecting xi minus 1, ti minus 1 to xi comma ti, I varying from 1 to dot 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 m lie in this interior of the domain ut. So according to, again, if we just follow the step 1, and since we are connecting, we connected firstly from x naught to y, and then we will further connect, then we will further connect, and we will reach to the bottom of the bottom of the cylinder u. So following the step 1, u is equals to m on each such segments, and so u is constant on the whole interior earlier than time t naught. So this t is less than or equals to t naught, earlier the time t not. So this is the global constancy of the function u of the solution of the heat equation u in case u is attaining its maximum value inside the domain ut, inside the domain on the interior of ut. In the same way, you can prove it for the minimum. If u is attaining its minimum value on the interior, then it is going to be constant. Next, talk about a remark, and we need to write a remark, and then we will talk about the uniqueness. The strong maximum principle implies that if u is connected and u is belonging to C1 to UT intersection C UT tilde satisfies UT minus Laplacian of u equals to 0 inside the interior of the domain and u equals to 0 on the boundary, and u has some function of x on the initial time t. This is a mixed condition, mixed initial boundary condition where z is greater than or equals to 0, then u is positive everywhere within ut if z is positive somewhere on u. So it is saying that you can say that u equals to gx is defined at the initial time t equals to 0. So if this function g that is coming from gx such that x is coming from u, because ut is u cross 0 comma t. So this x is coming from the u, and that is subset of Rn. So if z is positive somewhere on this domain u, then it implies that u is positive everywhere on the this domain. U is positive everywhere within this domain, like inside of this domain. Is this statement what is clear what it tried to say? Because I'm not going to give the proof. You can, okay, just let me what it is saying. Is this boundary condition clear?
Yeah.
So this gx is function of the spatial variable. So gx might be a positive definite function, might be a negative definite function, or might be a mixed function. Is not it? So it is not talking about the positive definite or negative definite. It is saying that if at any point of the domain u, z is greater than 0 for some x belongs to u, if this g is positive for some x belongs to u, then u is going to be strictly positive on the inside of the domain ut. In the same way, you can say that if z is negative for some y belongs to Rn, then u is going to be negative everywhere within this domain ut. Now is it clear what it tries to say?
Yeah.
Next, we are coming to the uniqueness on the bounded domains. Every time when we talk about the uniqueness of the heat solution, so always keep in your mind, by using the Tychonoff solution, we constructed a set of solution that was a set of infinite solution, but the problem was that it has an infinite boundary. As soon as we switch to the bounded boundary of the heat equation, in that case the solution is going to be unique. When we are taking an infinite boundary, we cannot talk about the uniqueness of the heat solution because the Tychonoff give a set of solution that was not unique. Do you remember that? Like this was a particular way to construct the solution. It was not a very known way, like we are not taking the separation of variable or any other way. But we know how he constructed and we could see that it has infinite solution. But this was for a very general heat problem. So later on, authors like mathematician got to know that as soon as we are restricting our boundary of the heat problem, in that case we are going to get the unique solution of the heat equation. So how do we prove that? Let's see. Uniqueness on the bounded domains. Never forget two things in your heat problem. Duhamel's principle, Tychonoff's theorem, and if someone is saying that the solution of the heat equation is unique, so that is wrong. And you know why? Because the solution of the heat equation is unique only on the bounded domains. So these are related. If it has unbounded boundary, then you can't talk about the uniqueness. If it has a bounded boundary, then you can talk about. And this uniqueness, next we will be studying the Wider's theorem. That is on the bounded domain. Yeah. Is it clear, Roberto? So uniqueness on the bounded domains. Camilo will give the proof of this theorem at this moment. Let G is belonging to C gamma T. Z is a continuous function defined on the boundary, and F is belonging to C u of t, and F is a continuous function on the inside of the domain. G is a continuous function on the boundary of the domain, and F is a continuous function inside the domain. Then there exists at most one solution U belongs to C1 2. So there will exist at most one solution. Either the solution will not exist, or if it exists, so there will exist at most one solution. That solution will be the second order derivative of the solution will be continuous on inside of the domain, and the solution itself will be continuous on the boundary of the initial or boundary value problem, defined as ut minus Laplacian of u is equals to f inside of the domain and u equals to z on the boundary of the domain. Now, can anyone give me the sketch of the proof of this theorem? This is similar of the uniqueness of the Laplace equation. Please tell me the proof.